Hello, I'm Richard Palethorpe and this is a video on the FuzzySync library, which is part of the Linux test project. We use the FuzzySync library to reproduce particular outcomes to data races. Usually the data races are in the kernel, because the Linux test project primarily tests the Linux kernel. So, in this video I will go through a contrived data race that happens in userland, which is easier for me to explain than an actual kernel bug or a data race happening inside the kernel. On the left here you can see an article I wrote on the same subject. I'll cover mostly the same material, although I may go a bit off-piste during the video and say some other stuff. Okay, so now I will briefly try to explain how an LTP test works. Each test is a standalone executable. The tests are written in C and they link into the LTP test library. The test library does things like declare the main function. So in our test, we simply declare a struct which has some callbacks in it, like setup, cleanup, run. And if you're familiar with unit testing libraries, then you probably recognize this stuff. And that's generally how LTP tests work. And this one's no different. So moving on to the specifics of FuzzySync. We declare a global variable which holds some state for FuzzySync. And then we initialize that in the setup function. And for this test, we change the default number of loops. And also here we have some setup for a statistics file we create a graph from, which I'll show you later. And then in our run function, we have some more boilerplate for FuzzySync. The pair reset function resets some statistics. If we run the main test function multiple times, and it also starts a worker thread which contains thread B. So we have a thread A, which is our main thread, and then we have a thread B, which we race against. We only have ever needed 2 threads, so we only have 2 threads support in FuzzySync. We've never needed 3 so far. So in each thread we have a main loop, which is controlled by the FuzzySync library. We have run A and run B, and these functions act as a gate or a synchronization mechanism. So when one thread enters run A or run B, it will have to wait until the other thread also enters run A or run B. And until later on, when we begin introducing delays deliberately, both run A and run B should exit at about the same time, which is different to some other synchronization mechanisms where both threads may, or one thread may exit sometime after the other. In FuzzySync, we avoid doing anything which may cause them to exit at different times, at least initially. That includes things like using a futex, which may sleep inside the kernel or cause a context switch. So we avoid those things. Of course, we can't guarantee that they both leave at the same time. Also, the run thread decides when we exit the loop. It counts the number of loops and checks how long the test has been running. If the test has been running too long or we've exceeded the minimum number of loops, then it will quit. And it also collects some statistics. Okay. Then we set our winner variable. The winner variable, which you can see on the right, is a volatile global variable, which is the center of our race. I'll come back to that in a moment. Then we have start race and end race. These demarcate our race window. So we have these in both loops as well. They also synchronize both threads. So when we set winner A here, we know that by the time start race B exits, winner will be set to A, because in both threads, start race is synchronized or gated. And then inside the race window, we have some logic, which forms our data race in A. And in B, we have a nano sleep, which wastes some time. And we simply set winner to B, which is a very simple store operation. The nano sleep just wastes some time, and I'll come back to that in a bit as well. Okay, so let's try and understand the data race. So if you look at this statement here, we can see we check if winner is equal to A and winner is equal to B, winner is equal to A. Now it may seem that this is an impossible statement. However, it is not, because there is actually a time gap between loading the value of winner to check if it's equal to A and loading the value of winner to check if it's equal to B. This is two separate statements. It's on the same line, but it's not the same statement, which is not always obvious to everybody. So the value of winner can change in the time that it takes to check that it's equal to A and load it again to check that it's equal to B. So the reason why I've declared the variable as volatile tells the compiler to treat this variable like it's an IO operation, roughly speaking. So the compiler won't look at this statement and say, well, I know that winner was just set to A, so this first part of this if statement here, this will always be true. And the second part of this if statement, this will always be false. So I can simply remove this statement. A is just a constant. As far as the compiler is concerned, I can just remove all of this code and just set it as a constant. However, setting the variable as volatile indicates to the compiler that this winner variable may change at any time, and if we set this winner variable, it may have side effects, which is roughly equivalent to saying that it's an IO operation like fprint, which writes out to a file. From the compiler's point of view, it doesn't know what loading and storing to winner, what effects those will have. So, going back to the data race, there are three possible outcomes from the data race. There are three sequences that can happen. The first is that winner is set to A, and by the time we load winner, thread B has not run yet. So thread B is still stuck in nano sleep or doing something else, or has been interrupted by the kernel for that matter and is not running at all. So in this case, we load winner, we see that it's equal to A. Then thread B is still not doing anything, it's still in nano sleep. we load winner again, and we see that it's not equal to B. Then thread A exits, or it reaches the ends race function and sits there spinning, and winner is set to B by thread B. So in this case, B wins. Then, in the second case, somehow thread B manages to complete nanosleep and set winner to B before A has even started. This can happen if thread A is not scheduled. If it's interrupted and not scheduled, then this can happen. In this case, we set winner is equal to B. Then thread A eventually runs and sees that winner is not equal to A, so again it exits and B wins the race. So in the first two instances, B wins the race. Then there is a final third option where we check if winner is equal to A. Thread B has not exited nanosleep yet and set winner is equal to B. So we see that winner is still equal to A. And then thread B manages to set winner is equal to B before thread A then checks if winner is equal to B. So it loads winner and finds that it is equal to B, and then we manage to set winner to A. So only in the third case does thread A win. And this is the case we're most interested in. And it is a difficult race outcome to reproduce because of the large amount of time that nanosleep takes up relative to the very short amount of time it takes to check if winner is equal to A. And it's also a very narrow race window because there are only a few CPU instructions between checking if winner is equal to A and winner is equal to B. Again, relative to the size of the nanosleep. So nanosleep only is set to sleep for 1 nanosecond, which is impossible on my computer. However, it still wastes a lot of time because it has to context switch into the kernel. So it will spend something like between 30 and 40,000 nanoseconds on my machine just going into kernel space and then coming back out again, which is far, far longer than however many nanoseconds it takes to perform this operation. And in fact, if we go and look at the article, you can see that I disassembled the output of the compiler. Somewhat surprisingly, the compiler split the if statement into 2 halves. And this move here is the first load. So the compiler actually loads the value of winner from memory and puts it in a CPU register. Then it compares that value with 41, which is the A character. And if it's equal to A, then it jumps to the second half of the statement, which is somewhere down here, and then loads the winner again. And so basically these two instructions plus whatever else the CPU decides to do in between the first and second move, that's our race window. Now let's run the test. You can see that fuzzy sync prints some statistics, some diagnostics, and the test doesn't take long to run. We usually give our tests, our data races, a bit longer to run than that. So moving on. And now here you can see some graphs where I've calculated the difference between the start of thread A and the start of thread B and graphed them. So on the left here, we can see that there's not much difference between the start of A and B to begin with. And then we introduce a random delay, and the start times then become much different. And the red dots you can see here are where thread A won the race, and each little black pixel is where thread B won the race. So I'll explain why we need the delay in a second. Moving down, we can see the differences between the end of A and the end of B. This is a little bit more interesting. You can see there's some more variation even before we introduce the delay. If you look very carefully, you can see there's some outliers going up to around about 10,000 nanoseconds. There aren't any around 0 nanoseconds, which is where A wins the race. But if we ran the test for long enough or ran it on enough different systems, then it would eventually hit the race even without the delay. But it would be very rare. And that is why we introduce the delay, to hit timings that do not happen very often. So let's go and look at a different graph. This is a more abstract diagram of what's happening. In the first half of the test execution, winner A runs and nanosleep runs. Nanosleep is not drawn to scale here, it is vastly larger than A. And so the probability of A lining up with B, winner is equal to A and winner is equal to B lining up, is very, very small. And instead what happens is that A enters the end function where it spin waits, and the end race function collects how many times it has to spin waiting for B and records how long it has to wait. And after some time, if the timings have a very fairly small deviation, then we'll try calculating a delay which will combine the thread A race window and the thread B race window in all possible combinations, so in all possible timings. So we will delay A up to the time that it takes to complete B altogether, plus about 10% for a margin of error, and we will delay B up to about the entire time it takes thread A to execute. And so at the bottom here we can see the ideal timing. The delay is chosen at random from all possible sane timings. But here we can see the perfect delay where winner A and winner B are synchronized, and thus causing A to win the race. So basically we just delay A for however long nanosleep usually takes. Now, in our contrived example, what we could do is just move nanosleep outside of the race window, and then we'd hit the race condition a lot more often, and in fact introducing a delay would probably be detrimental to reproducing the race condition. But this is only a contrived example where we have our data race in user land and in our test code. So if the data race existed inside the kernel or in some other library, we wouldn't have the fine-grained control where we can place start A and start B. And even if we did, because the kernel is changing all the time, it may be that the race window actually moves. So let's say that we have a race condition which is triggered by two different system calls, and the race window is near the beginning of one system call and near the end of another system call. We can get a similar scenario to this where thread A manages to enter the race window at the beginning of the system call long before thread B is able to reach the end of the other system call where the race window is for that side of the kernel code. And between kernel versions, that can change. So even if you could reach into the kernel and place a marker inside it, it may be that there's a slight change to the code which changes the position of the race window. Or I guess you could use BPF or something to reach into the kernel and set some markers, but then that is not ABI, is not using the ABI, so you would have to write a different version of the test for each kernel. Plus you would need root permissions for tests that, or capsysadmin for tests that wouldn't otherwise need it. So that's why we need to introduce this delay and why a random delay often makes a lot of sense. In some cases, we might be able to provide a hint to fuzzy sync that the race window is at the exit to one system call, but so far we've not needed to do that.